Okay. Can you see my screen?
Yes, we can.
Okay, perfect. So welcome to the final day of the QBrazil entangling workshop. So today we're finally going to be going over Grover search. So before I even jump into the content for today, just a quick reminder about Canvas. So ensure you've accepted the invitation and set up your account. And there is an assignment for each day. So the assignment for today will be unlocked after today's session. So endeavor to get at least 75% from all the assignments. So today we're going to be going over Grover search. But before I do that, I'll just quickly take a look at the notebook on phase kickback and multiple control constructions. Okay, so earlier we were looking at the controlled NOT operator or controlled operators in general. And we said that in such operators, we have like the control qubit or the control qubits, and there will be a target. So depending on the value of the control qubits, the target might be affected. So in the case of the control NOT operator, if the control qubit has a value of 1, the NOT operator is applied to the target. But here, with phase kickback, we have this interesting quantum effect whereby instead of the target being affected, it's the control qubits or the controller qubits. So we even implemented a circuit to show phase kickback. Okay, so this was the circuit we made use of. Okay, no, sorry, I tweaked something here. So this was the circuit we made use of, and we said we started off with the 0-1 state, and after implementing the circuits and checking our results, we got 1-1 at the end. So here, 0 is the control and 1 is the target. So 0 is the control and 1 is the target. But at the end, we have our control qubit with a value of 1. So the control qubit was the one affected instead of the target. And we looked at how this happens. So here we start off with the 0 state, and we apply a Hadamard operator, and we get the plus state. Then we have the 1 state, and we apply the Hadamard operator. Then we get the minus state. So here, okay, so here we have the 2 states, the plus state and the minus state. So at this point, we can apply the C0 operator. So it's when we apply the C0 operator that phase kickback actually occurs. And the way it happens is such that the control here has a value of 0. So the control has a value of 0, and the target is the minus state. So nothing happens to the control because it has a value of 0. And 0 will not trigger the C0 operator. But 1 here is going to trigger the C0 operator. So we have a control of 1, and the target is the minus state. So because the C0 will be triggered in this case, it's going to receive, the one state is going to receive a negative sign. So whatever is going to trigger the C0 operator and the minus state is the target, the phase kickback will occur and that state will have a negative sign. So now we have the minus minus state, and when we apply Hadamard operators, we end up with 1, 1. So there's another task here where we have 7 qubits, and we're to see phase kickback here. Okay. Okay, I think it might be fine at this point. So let me run this. Sorry, I think I made some edits here, and I'm not sure what I did. Nope. Okay. Okay, perfect. So here, we have our target qubit. So we set our target qubit to the minus state, and we apply a couple of HKs here to create an equal superposition. So for this location, we have the plus state. Also for this location, we have the plus state. And we're utilizing C0 operators here. So there's a 1 here and there's a 1 here. So when we apply C0 at these locations, phase kickback will occur and we'll get negative signs here. And then when we apply H once more, we'll have 1, 1. So every other location, we apply H consecutively and they just cancel themselves out. So every other location, we have 0. And here we're going to have a 1. So if we look at the results, we get 0, 1, 1, 0, 0, 0, 1. So because the target is the minus state and the plus state contains 1, so it's going to trigger the C0. So 1 at the location will receive a negative sign. That's why we get the minus state at these locations. So that's pretty much how it works. Whatever is going to trigger the C0 operator receives a negative sign. So let's move on to the multiple control constructions. So we also saw this yesterday, and we said for the C0 operator, when our control has a value of 1, then we apply the not operator to the target. But what if we wanted a case whereby if the control had a value of 0, then we applied not operator? So to do that, we use the operator you see here. And in our circuits, to implement this operator, we make use of the not operator. So we apply an X. So because we're starting off with 0, we apply an X, it becomes 1. Then this will trigger the not operator. And then finally, applying an X here will return this back to what it initially was. But we're starting off with 0 as our control, and that is what triggered the not operator. So we can also have multiple controls, as you can see here. So here we have 2 controls and the targets. So when we have 1, 1 here, we'll apply the not operator to the targets. When we have 0, 0 here, then we apply the not operator. And same thing works for the remaining 2 operators. And we can even have 3 controls. So for this operator, C naught, we can actually build it by utilizing the Toffoli gate, that's CC naught. And this is how we do it. So we introduce an auxiliary qubit here, where the auxiliary qubit becomes 1 when these 2 values are 1. So because we have a 1 here, if this is also 1, then we'll apply the not operator. So it's only when we have 1, 1, 1 that the not operator will be applied. So there are a couple of circuits here where we create multiple control gates. So here we're creating an operator with 4 controls. And we can even have variations whereby in the case described here, it's only when we have 1, 0, 1, 0 that the not will be applied to the target. So just by introducing X gates, we can decide the values that we want 0 we can decide the values that we want 0 to be. We can decide the locations in our inputs for which 0 can trigger the not operator. Okay, so let's move on to our main content for today, which is Grover search. Okay, so Grover search is actually unstructured search. So you can Grover search is actually unstructured search. So what I mean by this is, for example, let's say I'm trying to find someone in a crowd of people. So I don't know what this person looks like. And what I'm going to do is that I'm going to go around asking people for their names until I find the person I'm looking for. So in such a scenario, anyone in the crowd could have been who I'm looking for. And I'm just randomly going to start asking people. So there is no way to increase my chances of finding the person that's looking for. There's no way to increase my chances of finding the person I'm looking for. So in that case, like we have what I'm performing an unstructured search. And at an average, let's say there are n people in the crowd, I might have to go through n over 2 people before I find who I'm looking for. But let's say I'm really unlucky. I might even have to go through everyone in the crowd, and it's finally at the last person that I find who I'm looking for. So we're going to utilize Grover's search we're going to utilize Grover's search. So Grover's search is a quantum algorithm that can perform this search faster. So we're using Grover's search to speed up unstructured search in a quantum circuit. So if you're conversant with big O notation, unstructured search has unstructured search is O of n, whereas unstructured search in a classical setting is O of n. But if we're utilizing Grover's search, it's O of root n. It's O of root n. That is to say, in a classical case, let's say I had to go through a crowd of 1 million people. You can imagine how large that might be. And in the worst case scenario, it might be the last person. I have to go through 1 million people before I finally find who I'm looking for. But with Grover's search, the square root of 1 million is 1,000. And I'll be looking at going through 1,000 people, for example. Not necessarily the case, but let's say 1,000 people before I find who I'm looking for. So let's see how to implement Grover's search. Okay, so we have a simple game where we have n elements, and some of the elements are marks, and the marked elements are what we're interested in finding. So Grover's search consists of 2 phases, the query phase and the inversion phase. So in the query phase, we're going to mark an element. In the query phase, we're going to flip the sign of the marked element. So the marked element is what we're interested in finding, and we're going to flip the sign of the marked element. And then in the inversion phase, we're going to reflect all the elements about the mean. Okay, so in the first task here, we have 8 elements, and the fourth element is the marked one. So this is what the fourth element is what we're interested in finding with Grover's search. So we're going to utilize the bars here to see how Grover's search works. Okay, so if at any point in time you have a question, feel free to ask for clarification. So we've already said we have a list of 8 elements, and the fourth element is the one we're interested in finding. So as you said, Grover's search consists of 2 phases, and the first phase is the query phase, where we change the sign of the marked element. So as you can see, in the query phase, a negative sign is attached to the marked element. In this case, because the first element is the marked element and it's at location 3, we change its sign, which is what you can see here. So the marked element now has a negative sign. Then we move on to the inversion phase. And this is what happens in the inversion phase. So in the inversion phase, we flip all our elements about the mean. So from the bars we have here, what is our mean? So from the bars we have here, what is our mean? So this is something you can type in the chat. So most of our bars have a value of 1, and the marked element has a value of -1. So what is our mean here? Okay, so I'm seeing 3/4. Any other suggestions? Okay, so let me try and calculate this. So there are 7 bars here, all with a value of 1. And then we have -1. So if we divide by the total number, which is 8, we get 6/8, which is 3/4. So thanks a lot for that, Nicholas. Yes, the mean is 3/4. So if the mean is 3/4, then that's the line I'm drawing here. So if this is the mean, and in the inversion phase, which is the next phase, were to flip all the elements about the mean, or were to perform a reflection where the mean is the line of reflection. So what's going to be the new value of the first bar here? So if we perform a reflection about the mean, what is going to be the new size of the first bar here? So if anyone knows, feel free to type in the chat. So the first bar here, which has a height of 1. If we perform a reflection about the mean, what will be the new height of our bar? If anyone knows, feel free to type in the chat. Okay, so I'm seeing 1.75. Okay. Any other suggestions? I would guess 1/2 for the positive bars, 0.5. Okay. So let's see. So if we are to reflect about the mean, the tip is at location, it's at this location, 1. And if we reflect, it's going to go to the other side, and it's going to end up at this location, 0.5. So yes, 0.5 is the right location. And for the inverted bar, that's the marked element. Not the inverted, the marked element. What's the new location for the new size for the marked elements after we've performed an inversion, or after the inversion phase? What's going to be the new size for the marked elements? So any suggestions? Okay, 1.75. So let's try this out. We have this, and if we are to invert it, so from here up to this point, we have 1.75. So we have 0. We have from this point to this point, we have 0.75. And from here to here, we have 1. So we have 1.75. So if we turn this around, the length of our bar is going to be 1.75 from this point up until the line of reflection. But we also have 0.75 from the line of reflection all the way to 0. So if we are to add 0.75, the new location is going to be 2.5. So the location we have here is going to be 2.5. So let's see the results we have here. As you can see, the marked element is now at 2.5, and all the remaining bars are at 0.5. So we can perform another round. So we do query and inversion once more. So here, this is the query phase, and then inversion. And this is what happens. And we do it once more. Okay, I think we can stop here. So at this point, our bar is even higher than 2.5 after we performed query and inversion. So we have a second task here. So in the task here, we still have a list of 8 elements, and the 4th element is still the marked one. But now, instead of performing 2 rounds of the query and inversion phases, we're going to do this 20 times. So we have 20 steps of performing query and inversion. And we want to see how the marked elements will change through these 20 steps. So in task 2 here, we have our marked elements, which is the 4th element, and we're going to perform query and inversion. So the bars here are not the elements in our list, because we said we have just 8 elements in our list. And as you can see here, we have about close to 20 bars. Or even more, probably, I'm not sure. But we have a lot of bars here. And what we're doing is that we're showing the, okay, yes, so I think there are 21 bars here to show the 20 steps we want to do. So this is where we started off, and our marked element had a height of 1, or its size here was 1. And then we performed query and inversion. Then we ended up at 2.5, which is what you remember from the first task. Then we performed query and inversion again, and it's increased in size. Then if you perform query and inversion a third time, it drops in size, becomes negative, becomes even more negative, reaches the maximum negative point, and then it starts increasing once more. So it follows the cycle you see here. Becomes really high, becomes really low, becomes really high, and it just keeps following this the more times we apply query and inversion. Okay, so for the third task, we now have a larger list. We now have a larger list in the third task here, and the 11th element is the marked element. So in task 2, we had 8 elements in our list. So in task 2, we had 8 elements in our list, and the 4th element was the marked one. So in this case, it took 2 steps or 2 rounds of query and inversion to get to the highest point. So we performed query and inversion, we ended up here. Then we performed query and inversion once more, and then we ended up here. So it took 2 applications of query and inversion to end up at the highest point. But now we have a list with 16 16 elements, and the 11th, just a single element, is the marked one. So what do you think? Do you think we're going to use 2 steps or more than 2 steps, or less than 2 steps to before we reach the highest points, or before we get to the bar with the highest size? So before we get to the tallest bar, do you think we're going to use 2 steps or 2 rounds of query and inversion, or 2 or more than 2? Okay, so I think I have a question. Let me check and see. Okay. Someone is utilizing reflection here, 2m minus x, and it works. Yeah, perfect. We're even going to utilize that not too long from now. So nice job for thinking ahead. Okay. So 4. So I'm not really asking for a specific number. We now have, but we now have a list with 16 elements, so it's larger. It's twice the previous list. And do you think it's going to take less than 2 steps or more steps to get to the highest point? Any ideas? Okay, so it looks like no one no one knows. So let's take a look. So here, it takes more steps. Okay, yeah, true. Nicholas suggested 4, and he just might be right. Oh, perfect. It's actually is 4. And that makes perfect sense now that I think about it. Yes, so we we needed more steps before we got to the highest point. In this case, 4. Okay, so now we have a list with 16 elements and 3 marked elements. So what do you think? More steps or less? So we needed 4 in the previous round when we had 16 elements in our list. But now we have 3 marked elements. In the previous step, we had just a single marked element. The 11th element was the marked one. So we were interested in finding the 11th element. But now we have 3 elements. So more or fewer steps. Okay, so I think I'll just come in here and let's scroll down and see the answer. So in a single step, we were able to get to the highest points. So now that we have 3 marked elements, it took fewer steps to get to the highest point. Okay, so we have, although I've probably just shown you the answer, but hopefully you didn't see it. Let me try not to do that again. So here we want to figure out if the norm, the L2 norm, or the length of okay. So we have a list here with 16 elements, and we're going to use a vector to represent the we're going to store the sizes or the lengths of the elements in our list in a vector. And we're going to perform query and inversion a couple of times. Let's say 20, for example. Yes, 20. So do you think the length of our list, the length of our vector, or the L2 norm, do you think is going to be preserved? Do you think it's going to stay the same, which is 4, or it's going to change? So what do you think? Will query and inversion change the length of our list? Let me repeat this one more time. We have a list with 16 elements, and they are all going to start off with a size or height of 1. And if they all have a height of 1, then the length of our list, or the length of the vector containing the heights of all the elements, is going to be 4. If we are to perform query and inversion 20 times, do you think the length of our vector will stay 4, or it's going to change? What do you think? So we have our vector with 1s. So dots, dot, dot. All the elements in our vector all have a size of 1. And we perform query and inversion. So if we are to calculate the length of this vector, we have 4. So do you think it's going to stay the same, or? Okay, looks like no one knows again, or you just don't want to answer, but let's scroll down and see. So in the first step, we perform query and then inversion, and it stays for second, third. So for all the steps, we're performing query and inversion, and it stays for. So for the next task here, we're going to do the same thing. We have a new list with 10 elements, and we do the same thing, and it's the length of our vector stays the same. So query and inversion, they preserve the length of our vector. Great. Yeah, let's move on. So okay, so let's even look at global search algorithm a bit more, or the general structure for how it's going to work. Okay, so we have our list, and we're obviously looking for some elements, which we call the max element. And the thing is that, so let's say we had a list of people, and let's say we had a list of 4 people. John, Mike, Joy, Tess. I don't know. I'm just randomly coming up with names. So, okay, we have a list with 4 people. So we're going to assign an index to all these names. So we have 0, 1, 2, and 3. So to implement global search, first of all, we'll need to decide the number of qubits that we're going to use. So to do that, we're going to calculate log of n, where n is the number of elements in our list. So here we have 4 elements, and we want to calculate log n. So this is log base 2. And because n here is 4, log base 2 of 4 will give us 2. That means we need just 2 qubits for our list. So because we have 2 qubits, the states, okay, I don't think I've spoken about basis states. Okay, but these are the basis states. 0, 0, 0, 1, 1, 0, and 1, 1. So you can just think of the basis states as the binary values, like when we're counting. You can just consider those as the basis states. So these states represent the entries in our list, or these are the indexes for the entries in our list. And we now have an oracle to which we're going to point out the indexes. So we don't know the marked elements. We can't find the marked elements. We can't we don't know the properties of the marked elements, or how do I put this? To know the marked elements, what we're going to do is that we're going to ask an oracle. So you can think of an oracle as some spooky standing woman, or like the Matrix, for example, that you go to for questions. So, sorry, for answers to questions. And we're going to ask the oracle, is the marked element 0, 0, or is the marked element 0, 1, or is the marked element 1, 0, or 1, 1? So it's the oracle that will tell us the marked elements. All we do is provide the input values, and it's the oracle that tells us which of these is the marked element. And the oracle is going to work such that when we provide the input that is the marked element, the oracle will attach a negative sign to that element. So if joy was the marked element that we're interested in finding, the oracle will attach a negative sign there. So in our previous implementation, or in the bar chart we were drawing above, what we're doing is that we were already told the marked element, and we'll just multiply by, we were already told the marked element. Like, for example, in the first case here, we were told the marked element is the fourth element. And so we just attach a negative sign to the fourth element. But in actuality, to implement Grover's search, we'll need to construct an oracle whereby if we pass in the input values, the oracle is meant to be the one to check and attach a sign to the marked element or marked elements. So you should have some quantum mechanism detecting the marked element, and it will attach a sign to the marked element. So the thing is that in a classical scenario, or in a classical, if we were to implement this classically, what we're going to do is that because we have 4 elements in our list, we're going to be passing the entries one after the other. So you can think of it this way. Let's say we're interested in finding someone in a crowd, or someone in a crowd, or on a spreadsheet, for example. And we might ask our oracle, is the first person on the list, is that who we're looking for? So let's say we even told the oracle we're looking for Joy. And there's a spreadsheet, and we've told the oracle we're looking for Joy. So, okay, no, sorry, not that we're looking for Joy. The oracle knows that we're looking for Joy, and there's a spreadsheet. So we might ask the oracle, is the first person on the list, is that person we're looking for? And the oracle will check to see if it's Joy, and the oracle will be no. The oracle will be like, no. We'll ask, is it the second person? The oracle will say no. Is it the third? Then oracle will be like, yes. So we're going sequentially, like one after the other. But in a quantum circuit, we can actually create an equal superposition of all these states and pass it to the oracle. So you can think of this like just telling the oracle, which of the four people is who I'm looking for? And the oracle will be like the third, because oracle knows that we're looking for Joy. So instead of going sequentially, we can just create an equal superposition of all the indices. And we can just create an equal superposition of all the indices, and the oracle has some mechanism to attach a negative sign to what we're looking for. So okay. So the thing about Grover search is that when we were looking at the bars, so when we're looking at these bars, we said as we're applying Grover search, the amplitude of the marked element is increasing, and it will get to some high points and it will start decreasing. So what we're actually trying to do is do it enough times that the amplitude of the marked element, or the marked element, reaches the highest point, and that's where we stop. We don't want to continue beyond that point. So we'll need some way of figuring out the number of times to actually do this, to apply the number of steps of our phases. That is the number of times we should do the query and inversion phases, and just stop when the amplitude is at its highest point. So these are our phases, the query phase and the inversion phase. So we already know that for the query phase, we just attach a negative sign to the marked elements. And then in the inversion phase, we reflect about the mean. So we've already said that this is the form that reflection takes. So the mean here is our line of reflection, and this is what we intend on reflecting. So we can create our operator using this form. So this is the operator for reflecting about the mean. And the matrix here, it's for calculating the mean. So if we are to multiply this by a vector x, multiplying the matrix here with our vector x will give us the mean. And then when we multiply x with identity, we're just going to get x. Because if you think about it, all the entries here, they are all 1 over n. And when we multiply it by the entries in x and then sum it up, that will give us the mean. That will give us the mean. And we're just going to do that for all the rows here. So as you can see, when we multiply d by some vector x, we actually get our reflection of, we actually get 2m minus x, which is what we've already seen as reflection. Okay, so you can go over this and prove to yourselves that the transpose of d is still d and a square is equal to a. And also that applying this twice will give us the identity. So this operator is its own inverse. Okay. So let's move on to, let's continue like discussing global search. So we just briefly spoke about the operators and we've looked at the operator for the inversion phase. And for the query phase, we know that all the elements in the query phase, they just stay the same, except the element that receives the negative sign. So the matrix for our query phase will take some form that looks like this, where a negative sign will be at the location of the marked element. Or if you have multiple marked elements, we'll have negative signs at those locations. And so it will look like an identity matrix, but we'll have negative signs at the marked elements. So earlier we spoke of an oracle. So our oracle is just some function. And this is how it's going to work when we're discussing how to implement global search, or when we start discussing how to implement global search in more detail. So here, if the input we provide our function, so our oracle is some function, and if the input we provide it, if it's what we're looking for, our function is supposed to return 1. Whereas like for every other input, it returns 0. So for the marked element, if x is the index of the marked element, our function will return 1. But for every other case, our function is going to return 0. So we even have an example of something here that we might want to apply global search to. So for the example here, we have a decision version of the traveling salesman's problem. And here, so we have a traveling salesman, and he's starting off at A. So A is a city, let's say Amsterdam, for example. And he's supposed to travel to a couple of cities. So he's meant to visit all these cities and head back to Amsterdam, traveling the least possible distance. Or no, not the least possible distance. We're looking for a distance less than, let's say, 900 kilometers or 900 miles, something of the sort. So if we are to do this classically, we'll start looking for all the paths that we can take. So we might start off saying we'll go from A to B, A to C, C to D, and D back to A. That's one possible path, and we'll check the distance covered for this path. And then we'll check another path. So we might say A to C, C to B, B to D. So we'll be checking all these paths, looking for the paths less than 900. So we'll be checking them sequentially. But for Grover search, we can just create a superposition of all the possible paths and pass it to our oracle. And for paths less than 900 miles, a negative sign will be attached to those paths in the query phase. So this is like the difficult part of Grover search, actually creating an oracle that can do this. Okay, so if there are any questions, feel free to ask. If there isn't, I'm moving on to the next notebook. So here, we want to see what Grover search is. We're going to try and visualize Grover search using a single qubit. Okay, I think there is a question. Okay, is there a way to think about creating the oracle? Yes, kind of. I wouldn't say like I know everything there is to know about creating the oracle, but we've described the oracle as a function. We've described the oracle as a function f of x, where for the max element, it's going to return 1, and for the elements that we're not interested in finding, it's going to return 0. So we can actually create some Boolean functions utilizing, let's say, like the AND gates and OR gates like that. So we can actually create some Boolean function to do this. Yes, in a real case, f of x could really be hard, yes. We'll most likely need lots of qubits to implement a function f of x. Okay. So okay, so can this molecule be synthesized by this biological sequence in case of biosynthesis? Sorry, I'm not sure I understand the question, but let's say you are looking for a sequence amongst, let's say you are looking for a sequence amongst, sorry, let's say you're looking for a sequence for a specific sequence. If you can implement set function that will find that sequence, then you're good to go. So in that case, when your input is the sequence that possesses the right properties, the output is going to be 1, and the negative sign will be attached to that sequence. Okay. So now we're going to try and visualize Grover search on the unit circle, or we're going to try and visualize Grover search on the unit circle. So we have an axis here for the marked element, and we have another axis here for the unmarked element. Then here, what we have is the mean. So this is our list with 8 elements, and we have 3 marked elements. So these are our three marked elements: the 3rd, 4th, and 7th. So when we apply H gates to our 3 qubits, we're going to get an equal superposition of all the possible states. And we can split it into 2 here. So we have our unmarked elements and our marked elements. Then we represent them using vectors. So as you can see, for the, is this 3rd? No, 0, 1. Okay, so for the 4th, no, 0, 1, 2. Wait, this is the 3rd. For the 3rd entry, we have a 1. For the 4th entry, we have a 1. And for the 7th entry, we have a 1. So as you can see, at these locations, we have 1. We have 1s to represent these states. And similarly, for all these states, we have 1s at those locations. But what we have here, it's not a quantum state, because if we are using the unit circle and we have A0 plus B1, our basis states, 0 and 1 here, are valid quantum states. So if B here is the amplitude for this state, we want this to be a valid quantum state. So what we're going to do, so we want these to be valid quantum states. So we're going to do this. We'll factor out with 3 here, and what's left, we'll make it a valid quantum state. Similarly, we'll factor out with 5 here, and what we'll have left is a valid quantum state. And we can finally represent it in this form. So this becomes the amplitude for the marked state, and this is the amplitude for the unmarked state. And we now have what it takes to represent it on the unit circle. So you can even calculate it like this when it's in this form. So A and B, when we're initially starting out, will be the values 1/2√2, 1/2√2. But when we start applying the phases of Grover search, they'll start changing. Like they'll start changing. Okay. So these are the phases of Grover search, and we've now successfully created our marked states and the unmarked states. And the superposition will give us the state you see here. Then we can start applying our phases. So we'll apply the query phase, and we'll end up here. Then we apply the inversion phase, we end up here. We can apply query once more, we'll end up here, and inversion will end up here. So we can stop at this point because we're getting close to the amplitude for which the marks has its, we're getting close to the location where the mark state has its highest amplitude. Because if you think of the one state, for the one state, its amplitude will be 1 here. So similarly for the marks elements, when we get to this location, we're close to this point, and its amplitude will have a high value. And if we continue, let's say we perform like one more step, we might end up further away from where the marked element has its highest amplitude. So we're going to stop here. So we actually need to know how to figure out when to stop. We spoke about this earlier, and this is how we do it. So yep, we just take the square root of the number of elements in our list, but we have to multiply it by pi over 4. And from that, we will know the number of times to perform, or the number of steps to take. That's the number of rounds to perform query and inversion. But this is for a list with a single marked element. If you have multiple marked elements, k. So k could be 3, for example, as with the list we saw earlier. And this is how we're going to do it. So we have to divide the number of elements in our list by k before we take the square root. So in the complexity, so we spoke of big O of root n for Grover search. And this is how we get root n. It's by the number of steps we need to do, the number of steps for our phases. So we can even take a look at a couple of diagrams. So here, this is the initial state for the elements in our list. And then we can perform query, inversion, query, inversion, query, inversion, on and on. And as you can see, we start moving away from where the marked element has its highest amplitude. So what do you think? For the diagram you see here, after how many steps of query and inversion should we stop? After how many rounds or steps of query and inversion in this diagram do you think we should stop? So you can type in the chat. So does anyone know? Or performing query and inversion phases on the unit circle, as you can see. And after how many steps should we stop? So this is the starting point 0, query inversion. So this is 1, query inversion 2, query inversion 3, query inversion 4, and query inversion 5. So there are 5 steps, and which of these should we stop? Okay, so 3. Someone is asking 3. And yes, Cairo, this is where we should stop. It's the closest vector to the axis for the marked element. or yes, if I'll put it that way. So the state for the marked element is the closest state to that. And there are a couple of other implementations here. So as you can see, in the case you see here, we have up to 8 steps, or okay, no, even up to 10. So we set our number of steps here to 10. Number of iterations was set to 10, yes. And for this case, we'll probably stop somewhere around maybe 2 or 3. And we even have another case here, maybe up to 20 steps. And we're going to stop at most probably 8 for this. Okay. So let's move on to the next notebook. Or no, one more thing. Okay, so for our initial quantum states, before we start performing query and inversion. So where we said, okay, so up above, we said we have A and B, and A and B starts off with 1/√2. So A and B initially, they are 1/√2. And that's because we have 8 elements in our list. And when we take the square root of 8, we get okay, yes. When we take the square root of 8, we get 2√2. We get 2√2. So down here, we have our entries as 1/√n. So n is going to be 8 here, and we're going to have 1/2√2 as the amplitudes for all our states initially. So this is our initial quantum state. And then we can start performing query and inversion. So we've already seen the inversion operator. And 1/n here can be rewritten in this form. So earlier, we spoke about the dot product, and we used this notation for that, or the inner product. And we use this notation for that. So we said what we have on the left side is called a bra, and what we have on the right side is called a ket. We've been using a ket repeatedly for some time now. So the bra here is a row vector, and the ket is a column vector. So if we are to multiply these, we'll end up calculating the inner product, which will be some scalar value. So if we are to do the reverse, where we have a ket before the bra, we're going to have a column vector multiplied by a row vector. And we'll be performing the outer product in this case. And we're going to end up with some matrix, some projection matrix. And the matrix you see here is exactly what we have here. So we can replace this with our ket bra. So we just replace the matrix you see here with the QBronze notation. So we said the D operator here is written D because it's also called the diffusion operator. But it's the operator we use for inversion. And if we look at it being applied to some arbitrary quantum state here. So we have some quantum states which we're defining by using the mean or the initial, which we're defining using U, the initial quantum state, and another state orthogonal to it. So if you apply D to what you see here at the end, because we're reflecting about the mean, U will stay the same, but the states orthogonal to U will receive a negative sign. So I know I didn't really talk much about this. Normally, we've been using the 0 and 1 states to represent any single qubit quantum state. So we just have these in superposition with their amplitudes. But in actuality, we can use any states. We can use any two orthogonal states. So 0 and 1 are orthogonal. And here also U and the states are orthogonal to U. So we can also use this to represent any single qubit quantum state. So applying D, or okay, we're not even necessarily, okay, for any single qubit quantum state. So when we apply D here, U stays the same, but the states orthogonal to U receive the negative sign. Okay, so let's go on to the final notebook. But the main takeaway here, as I said, it's just that I wanted to point out the fact that we are representing D in this form, but it's still doing the exact same thing. It's the exact same operator, but we're representing it in this form. And if we are to apply it to some quantum states like this, for example, which has U, U will stay the same because U is on the mean, and this is reflecting about the mean. So U is on the mean, so U will stay the same, but the states orthogonal to U will receive a negative sign. Okay, so for the final notebook. Okay, so finally, we want to look at a circuit that will implement Grover search. And we've already spoken about the steps we've already given a general idea of everything that we need to accomplish this. So first of all, we'll need to decide the number of qubits that we're going to use. And it's such that if we're using small n qubits, so small n here is number of qubits, 2 to the power of n should give us the number of, or 2 to the power of n should be enough to contain the number of elements in our list. Then now that we know that we're using n qubits, we can apply Hadamard gates to all our qubits, and we can get a superposition of all the basis states. And they'll all have the amplitude you see here initially. Then we can start applying the query and inversion phases. So we said for the query phase, we're utilizing an oracle, and this is how the oracle works. If X is the max element or the element that we're looking for, it should return a 1, but in every other case, it should return 0. So we have a function here described by the table you see here. And this is the AND function. The function we have here is AND. So if our input is 0, 0, our output should be 0, 0, 1, 0, 1, 0, 0, and 1, 1. We have 1 as our output. But if you look at what we have here, if we're implementing the AND operator, we have 2 inputs and a single output. So if 0 is our output, how our circuit won't be reversible because we can't figure out which of these were the inputs provided that gave us 0 as our output, because there are 3 different possible inputs here that all have 0 as the output. So in this form, F is not reversible, and we want to implement this in a quantum circuit. So we need a quantum version of our we need a quantum version of our function here. And that's why we're utilizing U of F. So for U of F, our input's X here. So in here is X. We're going to pass X here, and we're still going to collect X at the other side. So we have an upper register here in our quantum circuit for our inputs, and it stays the same. But we also have a lower register for our outputs. So we have our output here in a lower register. And for our outputs, we're going to take Y XOR F of X. And initially, if Y is 0, and we take Y XOR F of X, we're going to get F of X. Because if we take 0 XOR anything, we're supposed to get that same thing. If we take 0 XOR anything, we're supposed to get that same thing. And if Y starts off with 0, we're going to get F of X. So we don't need to bother about this as long as Y starts off with 0 here. We would have successfully set up a quantum version of F here. So our quantum version of the function F is U of F here. So X and Y are the initial states of our circuit. And at the end, we have X and this. But because Y here is the 0 state, we're going to have X, F of X. So we can successfully collect F of X. Okay, but the thing is that when we spoke of our oracle, we said it attaches a negative sign to the marked element. It attaches a negative sign to the marked element. So in the case you see here, what we're actually interested in doing is attaching a negative sign to 1, 1. So to accomplish this, we're going to make a minor adjustment to the circuit you see here. So we're going to have to use phase kickback to attach the negative sign. So our minor adjustment is that instead of using 0 for Y, we're going to use the minus state. So we're going to use the minus state for Y. Okay, so we've set Y to the minus state, and we're going to implement, or we're going to try out U of F once more. So we're applying U of F to the initial state you see here. So U of F is distributive, so apply U of F to 0 and U of F to 1. So we've already seen, okay. We've already seen this, U of F applied to X and Y, then we get this. So that's exactly what we're doing here. So we're applying U of f to x0 and U of f to x1. And these are the final states after we've applied U of f. So at this point, we've already said f of x, XOR 0, we're supposed to get exactly f of x. And we've just brought this down here. Then we factored out the x. Okay, so at this point, there are two possible things that can happen. In one case, our output f of x. So our output f of x can be one of two things. Our output f of x can be either 0 or 1. So it has to be one of these two things. Our output f of x is either 0 or 1. So let's say f of x is 0. Let's see what happens when we have 0 here. So we replace f of x here with 0, then minus 0 XOR 1. So we have 0 minus 0 XOR 1. But if we already said 0 XOR anything, we'll get that same thing. So we're going to have 0 minus 1, which is what we have here. So if f of x is 0, 2 minus 1 to the power of 0 is just 1. So we have 0 minus 1 successfully. And in the other case, if f of x is 1, we're going to have 1 minus 1 XOR 1. So I know I'm saying like a lot here, but the recording we've made available. So if you go over the content and you watch the recording, it will be quite easy to follow. So if we take the XOR here, we're going to get 0. So we now have 1 minus 0. So if we were to factor out the negative sign, we're going to get 0 minus 1. 0 minus 1. So the negative sign here in front hinges on the value of f of x. So if f of x is 1, there should be a negative sign, and 0 minus 1 still stays 0 minus 1. So we've successfully been able to execute phase kickback. So this is the minus state. So from everything here, as you can see, we have x and the lower register is in the minus state. So when I apply U of f, depending on the output f of x, we either have the negative sign or not. So for values of f of x, for which the output is 1, there will be a negative sign, which is what we were interested in. So 1, 1 here, because f of x for 1, 1 is 1. 1, 1 will have a negative sign. So we've successfully shown how to utilize phase kickback in the circuit. So that's the first phase, the query phase, and we can move on to the inversion phase. So as you can see, this is the matrix for the query phase, and at this location, so this is an identity matrix, but we have a negative sign here at the location for 1, 1. Okay, so we can move on to the inversion operator. So if there's any question at any point in time, feel free to ask. So now, in the inversion operator, this is how we're going to implement it. So we have an ancilla qubit similar to what we saw in phase kickback. This is our lower register. It has the minus state. And then we're going to apply H gates to all our input qubits, then X, a multiple control not operator, X, H, X and H. So we've already seen this operator as our diffusion operator. So what we're doing here should implement this operator. And let's see how. So this, we have already rewritten it in this form. So U is the equal superposition state. So when we start off and we apply H gates, we're starting off with all our qubits in the 0 state, and then we apply H gates. And after doing that, we're going to get U. So we have U at this point. Then we've already written D in this form also. So because we already know that U is what we get by applying H to all our qubits in the 0 state, we can just rewrite U as this. We can just rewrite U like this. So U just involves applying H to 0. So for the identity here, we already know that the Hadamard gate is its own inverse. So applying the Hadamard twice in a row will give us identity. So we can replace identity with applying the Hadamard twice in a row. And we can just factor out the H. So the first H here and the first H here is what we have on the left. And then the other H here and the other H here. That's what we have on the right. Okay. So if we are to do that, this is all we have in the middle. So if we scroll back up, we've already seen that we're surrounded with H gates. So we're meant to start off by applying H gates, and we're meant to end by applying H gates. So we've already seen those H gates by the side. So what we have in between is supposed to help us implement this. So if you look at the operator here, we've already seen the case whereby we said this. We said this is reflection about the mean, and U is the mean. So if we write it in this form, that means we're trying to perform reflection about the 0 state. So we're trying to perform reflection about the 0 state. And let's see how to accomplish that. Okay, so we have, okay, we're just seeing it's actually happened. So if I apply this operator to the 0 state, 0 is going to stay the same. And if you apply it to any other basis state that is not the 0 state, they all receive a negative sign. So for our okay, so for the index 0, 0, as you can see, it stays the same. But for everything else, if we are to apply this operator, they will all receive the negative sign. So that's our operator here, G of X. So G of X, for the 0 states, its output is 0, meaning nothing happens. But for every other state, we want the output to be 1. For every other state, we want the output to be 1, so that they all receive the negative sign. So we'll just implement phase kickback here also, where the target is the minus state. The target, or the lower register, that's our ancilla qubit, is the minus state, and we have the negative sign here. So the thing is that this is a bit difficult to implement. So what we're going to do is that we're going to look at a difference operator here. And for this operator, it's actually the 0 state that gets negative sign, and everything else stays the same. So we have another operator here, G prime, where, as you can see, for the 0 state, the output is 1, meaning it gets the negative sign. But for all the other states, the output is 0, and they stay the same. So let's actually look at a circuit that we apply Grover search to. Okay, so here we have the query phase, and we said the operator that we're implementing is the AND operator. So we said we're implementing the AND operator, and we already know that for AND, when both of our input values are 1, then the output is 1. So here we have a Toffoli gate with 2 controls and the target. And the target has been set to the minus state. So when we have a 1, 1 here, we're going to trigger the Toffoli gates, and 1, 1 will receive the negative sign. But for everything else, 0, 1, 0, 0, 1, 0, none of them are going to trigger the Toffoli gate or CC not here, and they are all going to stay the same. So this is our query phase, and this is the oracle that has been implemented for the AND operator. Then moving on, we have the inversion phase here. And we said for our inversion phase, we're surrounded by a couple of H gates. So don't bother about this. This is just to set the ancilla qubit, or the lower register. Okay, I guess I should have just, anyway, this is to set the ancilla qubit here to the minus state. And this is just what returns it back to the 0 state. So we apply X and H to set it to the minus state, and we're applying H and X here to return it back to 0. So I will also, so let me just like border this out. Okay, so this is what sets it to the negative. This is what sets it to the negative state, and this is what sets it back to the 0 state. We've already seen the H gates. So this is what creates an equal to proposition, and we apply H at the end. So we've already seen that. Okay, so now this is what we have left. And we said that for our operator G prime works such that if the input is the 0 state, the output is 1. So for the 0 state, it's supposed to receive the negative sign. For the 0 state, it's supposed to receive negative sign, and everything else stays the same. That's how G prime works. So here, if we have 0, 0 coming as the inputs, we'll apply a couple of X gates, and the 0 here will become 1. And that's what will trigger the CNOT operator you see here. And 1 here will get the negative sign. And then we apply a couple of X gates. So these X gates will return this back to 0, 0. So it's 0, 0 that receives the negative sign. When we apply the X gates here, we apply the Toffoli gates, and then we apply these two X gates. But now we have another X gate here, and that is because G prime is the exact opposite of G. So G prime is the exact opposite of G. So as you can see, when we apply, when the 0 state is the input, G prime will produce 0 as the output. Sorry, when the input is the 0 state, G will produce 0 as its output, but G prime will produce 1. And for everything else, G will produce 1, and then G prime will produce 0. So having an X gate here just moves us from G prime to G, because if our output was going to be 0 here, if you apply an X gate, it will become 1. But if our output was going to be 1, applying an X gate here will make it 0. So X here just takes us from G prime back to G, because it will just flip the output it just flip the output. Okay, so this is our inversion operator. And now we can test out the circuit. So this is our circuit. This is our circuit. So we start off with a couple of H gates to create an equal to proposition. And then we have this to create the minor state. And this is our oracle that implements the AND operator, or f of x here is the AND operator. And then finally, we have our inversion phase. So we have the H gates that we start off with and the final H gates. So they are all here. We start off with a couple of H gates, and then we end with a couple of H gates. It's also here. We have H gates here and H gates here. So if I was to go back, we have H gates here and H gates here. Then we have everything in between. So we said this will successfully attach a negative sign to 0, 0. But because if we've put an X here, it's going to flip the function around, whereby everything else that is not 0, 0 will receive the negative sign. So this is how we implement the inversion operator, and then finally we can measure at the end. So every single time we measure, every single time we measure, we get 1, 1, because 1, 1 is obviously what we receive the negative sign when we query. So we have the query phase, and when we have 1, 1 here in the query phase, it will receive the negative sign. So this is the marked element, and this is just the inversion phase, where we are going to invert about the mean. So we even have another circuit here. So we have another circuit. So this has 3 input qubits. So our upper register here has 3 qubits, and the lower register, or the ancilla qubit, has just a single qubit for the minor states. And we have an auxiliary qubit here because we have 3 controls. We have 3 controls, so we're using an auxiliary qubit here. which is what we saw earlier in the multiple control constructions notebook. So here, if we have 1 1 0, 1 1 0 is what will trigger the controlled operator here. So X will make this a 1, and when we have 1 1 1, it will trigger the CCC not, and the phase will get kicked back. So here, okay, not 1 1 0, 0 1 1. So 0 1 1. And then we have our inversion phase here. So because there are 8 there are 8 elements in our list. So there are 8 elements in our list. So if we take the square root of 8, we're going to get 2 root 2, and then 2 root 2 will multiply by pi and divide by 4. So if you multiply 2 root 2 by pi and divide by 4, let me test this out, see what we get. So 2 root 2 divided by 4 multiplied by pi. So it gets about 2.2. We get about 2.2. And if you just round this down, we're going to get 2. So we're going to have 2 steps of query and inversion. So here, so here we have our first step of query and inversion, and the second step of query and inversion. And finally, when we measure, we get 0 1 1. The probability of measuring 0 1 1 is pretty high, and all the rest are low, because for the marked elements, so for the marked elements, we're going to come like really close. So there's a high probability of measuring the marked elements as against the unmarked ones. So these have a lower probability of being measured as against the marked elements, which is 0 1 1. After we've performed 2 steps of query and inversion. Okay, so that's pretty much it. I don't know if there are any questions. Yeah, sorry, I know I blabbed a lot today.
Thank you, Kenneth.
Yeah, thank you, Yanis. So the notebooks are available to you. You can take your time and go over them. So thank you. I guess I'll hand over to Johannes and the Q Brazil team if they have anything to add.
For Bruna have any comments, but I'm really thankful for the keyword team. Kenneth, you nailed the lecture. It was really, really enjoyable to have you here this week. And all the attendees as well. It was just great. Don't know if Rodolfo wants to compliment.
Yeah, I mean, I agree with everything you said, Chrisia. Thank you, Kenneth. Thank you, Ioannis, as well, for the support.
And thank you guys for
Um,
being here all the time.
yeah. And also, I would like to tell the attendees that so I think we have 1 extra week for the assignments to be done. Correct me if I'm wrong. But the QBrazil team will be available on Discord to answer questions there in the meantime, for sure.
Yes, and please try the questions so you can get your diplomas. So now we keep it up in Discord. Thank you all for participating and see you soon again.
Thank you all.
Thanks, everyone. Bye-bye.
Bye, guys. I'm stopping the recording now.
Great.
All right.